Hello, now that you did your first learning, we will study more in details a simple supervised learning algorithm, the k-nearest neighbors, or KNN. This algorithm is rather intuitive when the data can be represented as single points in a 2D space plotted on screen. We will choose a configuration with only two sensor inputs, the two superpixels from the camera. Let's start by connecting to the robot. To have the best contrast possible, place it on a white surface for the arena and limit the daylight by going away from the windows. From the starting configuration, select the camera mode Personalize 2 pixels in the Sensor tab. You should see a 2 pixels picture appearing, but you can select the Visualization tab and uncheck the Network Input Resolution. These 2 pixels are the averaged values of the two regions of interest. Now deactivate the speed sensor. We have 6 input neurons, 2 pixels for each red, green and blue channels. Select the green-red precomputation that highlights the red area and only has 2 input neurons. If you have an arena with a different color, try gray levels instead. Let's also simplify the actions to only keep straightforward, rotate to the left and rotate to the right. Select the option Pause between actions for a more reliable learning. We can finally choose the supervised learning algorithm k-nearest neighbors. You should see a graph appearing on the right-hand side and the 3 arrows changing colors. Instead of setting manually those parameters, you could have loaded the file Supervised Learning KNN Camera. Let's start with the training phase. Just as in the race, disable the autonomous mode. Start and click on the arrows to steer the robot. The graph gets a new point every action. The XY coordinates represent the left-right pixel intensity and are framed by the color of the selected action. Purple for right rotation, white to go ahead, and cyan to rotate to the left. Those points make up the training dataset. When the robot gets closer to the wall, the pixels become darker like this. Normally, if the left pixel is darker, the robot should turn to the right, and if the right one is, it should turn to the left. The largest point indicates the current picture from the camera and the action suggested by the algorithm. It is the most selected action from its k-nearest neighbors from the training dataset, which are linked with lines. For now, there is only one link, because the number of k-neighbors is equal to 1, but you can increase this number in the AI tab. This will increase the number of linked neighbors, which can change the suggested action. The more we add points to the dataset, the more we see the 3 regions forming, each corresponding to a certain decision. If you don't see the 3 regions forming, steer the robot with more care and make sure the luminosity is homogeneous. You can now go from the training phase to the test phase, also called the usage phase, by turning the autonomous mode back on. That's it. The robot avoids collision by itself. Let's now test the effects of changing the number of neighbors k to see which one gives a better behavior to the robot. We can, for instance, see here it makes less errors with k equals 3, because by increasing k, we reduce the effects of mistakes that can exist in the training set. To recap, the KNN algorithm used the Euclidean distance from the training dataset to generalize decision-making in regard to new data. Its main advantage is its simplicity. However, the computation time rises drastically for larger datasets, and Euclidean distance is not appropriate for more complex learning, such as face recognition.